A-level mechanics, elastic strings, energy. Let's have a look at how we can store energy in an elastic string. One of the assumptions we made about elastic strings is that the work done in stretching the string is stored in the string and can be regained as the tension is removed. For example, if we put a stone in a catapult and stretch the elastic back, once released the stone will fly out with quite a speed. The energy used in stretching the elastic string is stored until it's released, and then it's turned into kinetic energy in the stone. So, to calculate the energy stored in an elastic string, we need to calculate the work done in stretching it. The problem is the tension changes as the string is stretched. So, with a continually changing force, we can't simply multiply the force times the distance. One way to try to get round this is to multiply the distance with the average force. Suppose we have a string with stiffness K which extends by an amount x under a tension T. Then let's consider two cases, before it's stretched and once it's fully stretched. Now before it's stretched the tension is 0, and once it's fully stretched the tension is Kx. So we could take the average tension as 0 plus Kx divided by 2, or Kx over 2. Now if we assume we've got a constant average tension of Kx over 2 and extend it an amount x, the work done is Kx over 2 times x, or a half Kx squared. So the elastic potential energy would be a half Kx squared. The problem with that method is we assume that the tension is the average of the first and last tensions, whereas actually the tension is continually changing all the time. So a second method would use calculus. Suppose we partially extend the string by an amount s. The tension in the string will then be F, where F is equal to Ks. Now suppose we extend the string further by a very small amount delta S. We can assume the tension stays the same just for that very short period. So the work done in stretching the string by delta S is F times delta S. Now we want the sum of all such small stretches, but we also want the limit as delta S tends to 0. And so that is actually the integral of f ds between the limits 0 and x. But f is equal to Ks, and so we want the integral of Ks ds between 0 and x. Well, when we integrate Ks, we get Ks squared over 2 between the limits 0 and x, which gives us a half Kx squared. So we have the elastic energy stored in a string with stiffness K when stretched an amount x is a half Kx squared. And similarly we can show the energy stored in a string with natural length L and modulus of elasticity lambda when stretched an amount x is lambda x squared over 2L. So now we have two important results. If we're given the stiffness K of a string, then the elastic potential energy is a half Kx squared. If we're given lambda, the modulus of elasticity, then the elastic potential energy is lambda x squared over 2L. Let's have a look at an example. A toy gun fires a pellet of mass 7.5 grams using a light spring of stiffness 3 newtons per meter, compressed by 20 centimeters. Find the velocity of the pellet leaving the toy, assuming there's no friction. Now to solve this, we must remember to put all units in meters and kilograms. So 20 centimeters is 0.2 meters, and 7.5 grams is 0.0075 kilograms. Let's draw a diagram. Now the energy stored in the spring is a half Kx squared, which in this case is a half times 3 times 0.2 squared, which is 0.06 joules. Now if we look at the bullet as it emerges from the gun, suppose it's got a velocity v, then after firing the energy of the pellet is a half mv squared, which is a half times 0.0075 times v squared, and we're told that's equal to 0.06. Now that can be rearranged as v squared is 2 times 0.06 divided by 0.0075, which works out to be 16. And so v is the square root of 16, which is 4, and that gives us the speed of the pellet emerging from the gun is 4 meters per second. Example 2. A bungee jumper of mass 80 kilograms stands on a bridge and is attached to a light elastic rope of length 20 meters and modulus of elasticity 1,960 newtons. The other end of the rope is attached to the bridge at the same height as the man. When he jumps from the bridge, find the lowest point he will reach. Well, we can solve this using energy, but first we have to decide where is the zero for potential energy. So let the zero height be the top of the bridge. And then using the conservation of energy, the initial elastic and potential energy must equal the final elastic and potential energy. Now initially the rope is slack, so there's no elastic energy. Also, we're taking the top of the bridge as zero height, so there's no potential energy. At the lowest point, the elastic energy is lambda x squared over 2L, and the potential energy is mgh. Lambda is 1,960, and L is 20. M is 80, and h is minus 20 plus x. Now, 1,960 divided by 2 times 20 is 49. So we have 49x squared equals 80 times 9.8 times 20 plus x. In other words, x squared is equal to 80 times 9.8 times 20 plus x over 49, and that cancels to x squared is 16 times 20 plus x, or x squared minus 16x minus 320 is 0. Now, that's a quadratic equation. We can solve it using the formula, or we can just solve it straight away using a calculator. And we get x is equal to 27.5959, or x is equal to minus 11.5959. Now, we can't have a negative extension with rope. We can have a negative extension with spring. It'll be in compression, but that's not what we've got in this situation. So the lowest point is when the extension is 27.5959, and when we add on the natural length of the rope, this gives us a lowest point of 47.6 meters below the bridge. In example 3, we're told a catapult is made from a Y-shaped piece of wood with 2 elastic strings of length 10 centimeters and modulus of elasticity 12 newtons. The elastics are connected to the wood at 2 points 18 centimeters apart. A pebble of diameter 2 centimeters and mass 20 grams is placed in the catapult, which is pulled back horizontally 30 centimeters behind the wood. In part A, we're asked to find the energy stored in the elastics. Well, to solve this, first of all, draw a plan view of the stretched catapult. Now the diameter of the pebble is 2 centimeters. This gives us that AC is 8 centimeters. The pebble is pulled back 15 centimeters, so we can work out the length of the stretched elastic. Now to do that, we can use Pythagoras' theorem. In the diagram, AB squared equals AC squared plus BC squared. So AB squared is equal to 8 squared plus 15 squared, which is 64 plus 225, or 289, which means AB is the square root of 289, which is 17. Now the natural length is 10 centimeters, so that means the extension is 7 centimeters. Now we know the elastic potential energy is lambda x squared over 2L. Now in this case, lambda is 12, and working in meters, x is 0.07, and L is 0.1. So we've got 12 times 0.07 squared over 2 times 0.1, and that works out to be 0.294 joules. However, that is the elastic energy in one string. Now the catapult is made up of 2 strings, and so the elastic potential energy is twice that, which is 0.588 joules. So the total elastic potential energy is 0.588 joules. Now in part B we're asked, when the pebble is released, find the speed it leaves the catapult. Now we know the kinetic energy of the pebble after it's released is a half mv squared, which is a half times 0.02 v squared, which is 0.01 v squared. So from conservation of energy we have 0.01 v squared equals 0.588. If we multiply both sides by 100, we get v squared equals 58.8, or v is the square root of 58.8, which is 7.668. And so we have the speed of the pebble after it's released from the catapult is 7.67 meters per second. In example 4 we have a light elastic rope of natural length 10 meters is attached to a fixed point A, and the other end is attached to a block of mass 9 kilograms. When the block is hanging in equilibrium, the length of the rope is 10.6 meters. In part A, we're asked to find the modulus of elasticity of the rope. Now to solve this, the first thing to do is draw a diagram and then mark in the forces. There's the weight, which is a force of 9g downwards, and there's a tension in the elastic rope, we can call it T, upwards. Resolving vertically, we get T equals mg. So, using Hooke's law, which is T equals lambda x over L, we've got 9g is equal to lambda times 0.6 over 10. We can multiply by 10 and divide by 0.6 and get 9 times 9.8 times 10 divided by 0.6 is equal to lambda. And that works out, lambda is 1470. And so we have the modulus of elasticity, lambda, is equal to 1470 newtons. We're then told the block is pulled down to a point 13.6 meters vertically below A and is then released from rest. It moves upward and next comes to rest at a point B with the rope slack. Find the distance AB. Now we can solve this by using energy. So first of all draw a diagram, and then we must choose where our zero potential energy is. So let's take zero height as the lowest point, 13.6 meters below A. Now initially the block is pulled down 13.6 meters, which means the extension is 3.6 meters. So the initial energy is only the elastic energy in the string. So that's lambda x squared over 2L, which is 1470 times 3.6 squared over 2 times 10. And that works out to be 952.56 joules. Now, when the block comes to rest again, there's no kinetic energy, no elastic energy, and so the final energy is only gravitational potential energy, mgh. So that's 9 times 9.8 times h, which is 88.2 h joules. But we know the energy has been conserved, so using conservation of energy, 88.2 h is equal to 952.56. Now we can divide both sides by 88.2, and that gives us h is equal to 10.8 meters. Now that means the block is 10.8 meters above the lowest point. So that means AB is 13.6 minus 10.8, which is 2.8, and so we have AB is 2.8 meters. That means the block is 2.8 meters below A.